3i Atlas keeps finding new ways to surprise us. This time, it's not about its trajectory or speed, it's about the light coming from within it. When astronomers examined its coma, they didn't just see reflected sunlight. They saw illumination patterns unlike anything recorded from other interstellar visitors. Bright points, shifting glow, something active and evolving. In this video, we'll break down what that illumination could mean and why it matters right now. As we've discussed in earlier videos, 3i Atlas isn't just another object drifting through the solar system. It's only the third confirmed visitor from outside our star system, joining the very short list that includes Oumuamua and Borisov. And that alone places it in a category where every detail matters. These objects don't behave like the comets we're used to. They weren't formed here. They didn't grow up in the same cloud of dust and ice that created Earth, Jupiter, and the rest of our system. They come from somewhere else, somewhere we've never seen directly. For a while, researchers thought they had a general grasp of how Atlas fit into that. An icy interstellar traveler, warming as it passed near the sun, shedding material, forming a coma, and eventually fading out as it continued its path back into deep space. A rare object, yes, but still something that could be described with the same general rules used for comets in our neighborhood. But the more data that came in, the more that comfortable explanation started to slip. The chemistry didn't line up. The behavior didn't line up. And now, as we're seeing illumination patterns coming from inside the coma itself, even the structural assumptions are breaking. The key thing to understand is this: interstellar visitors are already rare, but ones that remain active this far into their journey are even more so. Most should be exhausted, stripped, eroded, inert. But Atlas isn't fading into silence. It's responding to its environment. It's releasing material in ways that suggest internal complexity, layered chemistry, and processes we don't usually see in standard comets. It arrived as an outlier. Now it's becoming something even more intriguing, a messenger from a system we haven't met yet. When astronomers first began tracking Atlas's motion, everything looked straightforward. Its path through the solar system was calculated, its projected trajectory mapped, and the numbers were expected to fall in line with the usual gravitational influences from the sun and surrounding bodies. For a while, they did. The movement was smooth, predictable, the kind of orbital curve you'd expect from a visitor simply passing through. But then, the data started to drift. Not dramatically, not enough to set off alarms, just enough to make researchers look twice. Small changes in velocity that didn't match where the comet was in relation to the sun. Slight decelerations where it should have been gaining speed. A gentle turning of direction that didn't correspond with any major gravitational source nearby. At first, these readings were easy to dismiss as observational noise or early calculation margins. But the deviations continued, and they were consistent. The trajectory didn't wobble, it didn't fluctuate wildly. It shifted with precision, almost as if the object were responding to something. A correction here, a subtle alignment there. Not random, not chaotic, structured. This is where the confusion deepened. Comets don't guide themselves. They don't adjust course. They are at the mercy of the forces acting upon them. Gravity, heat, solar radiation, outgassing. But Atlas was behaving like something aware of those forces, adjusting to them rather than simply reacting. Teams compared data from different observatories to rule out instrument error. The pattern held. They reviewed past interstellar visitor motion records. Nothing aligned with this behavior. Even the irregular accelerations seen in Oumuamua didn't match the pacing and form seen here. The change wasn't violent. It was controlled. Whatever was influencing Atlas was doing so gently, but undeniably. But the real shock came when James Webb looked directly at it. The first images didn't look unusual at a glance, just a bright coma, a faint tail, the standard signature of a warming interstellar traveler. But once the infrared layers were analyzed, something stood out immediately. Sections of the coma weren't merely reflecting sunlight, they were emitting light. Small regions that intensified and faded, almost like shifting embers within a cloud. At first, the assumption was scattering or dust alignment, something harmless, something known. But the patterns moved. They weren't random. and they didn't match the normal behavior of gas escaping from a surface. The illumination seemed to come from deeper inside the surrounding haze, closer to the nucleus, as if internal regions were releasing energy in pulses. Then, the chemical breakdown data was compared, and this is where it connected back to things we've talked about before. Atlas has always shown a chemical profile unlike most comets in our system, but this time, the imbalance was even clearer. Carbon dioxide dominated the signatures, while water vapor was unusually low. Not slightly, significantly. This isn't something we'd expect from a body that formed in conditions similar to ours. Water ice should be one of the first materials to sublimate as it warms. But here, carbon dioxide, the compound that normally fades or releases later, was taking the lead. It suggests either a different birthplace, a different layering structure, or an internal environment we don't fully understand. And when you pair that chemical imbalance with the shifting pockets of light, it begins to look less like a uniform object shedding material and more like something layered, structured, or compartmentalized. Not artificial, not deliberate, but active in a way that implies it still holds deeper reserves, deeper reactions, deeper history. In previous videos, we mentioned Atlas had more to reveal. This glow is the clearest sign of that yet. The illumination alone would have been enough to raise questions, but the chemical breakdown added another layer entirely. Alongside the carbon dioxide dominance, researchers detected nickel vapor and cyanide-bearing compounds in proportions that don't match the patterns seen in comets formed in our own system. These elements aren't unusual by themselves. Nickel and cyanide both appear in some solar system comets, but the ratios here are different. The balance is skewed, almost as if the material was shaped under conditions we don't typically see close to our sun. There are a few natural explanations scientists consider first. One possibility is deep radiation processing during the object's journey through interstellar space. Over millions or billions of years, intense cosmic radiation can restructure molecules, strip away surface materials, and alter what remains. Another possibility is that Atlas formed much farther from its original star, in a zone cold enough that carbon dioxide froze long before water. In that environment, CO2 would naturally dominate the volatile composition, and water might be trapped deeper beneath the surface or lost over time. There's also the idea of layered internal ice. If Atlas has a crust or insulating shell, the carbon dioxide could be escaping first while water remains sealed below. This would explain both the unusual chemistry and the shifting illumination we saw earlier. But then there's the speculation, handled carefully because it's just that, speculation. Some researchers have commented that the patterns in the illumination and outgassing look organized, or at least structured. Not artificial, not deliberate, but structured enough to make people ask whether there's more going on beneath the surface than chaotic melt-off. No one is claiming this is artificial, no one is suggesting technology, but the conversation is happening. Because whenever nature produces something that looks arranged, we're forced to consider how many possibilities we're willing to rule out before we understand what we're seeing.
If there's one idea that keeps coming up when scientists discuss Atlas, it's the possibility that something inside it is still active. Not alive, not conscious, just physically dynamic in a way that hasn't yet burned out. Remember, most interstellar objects should be exhausted by the time they reach us. Their surfaces should be stripped, their volatiles depleted, their reactions long faded. But Atlas is behaving like something that still has layers to expose. One explanation is subsurface heating. As the object approaches the sun, warmth can penetrate cracks and cavities below the surface. If pockets of volatile materials are buried deep enough, they could release gas in bursts rather than steadily. This would create uneven illumination and shifting coma activity, exactly what we're seeing. Another possibility involves volatile reservoirs that formed differently from those in our solar system. If carbon dioxide ice sits closer to the surface while water is locked deeper beneath, the early stages of heating would look inverted compared to what we know. Carbon dioxide would dominate first, creating that unusual signature, while the water remains untouched until much later, if it ever emerges at all. Then there's the idea of thermal fracturing. As Atlas heats unevenly, its internal structure could expand and contract at different rates. That stress can open new vents or close old ones, causing the glowing areas to shift and pulse over time. Instead of a uniform release, the activity would flicker, almost rhythmic but not controlled. Each of these explanations points to the same conclusion. Atlas is not simply eroding from the outside, it's reacting from the inside, layer by layer, revealing materials that have been sealed away since long before it entered our solar system. This means we're not just observing an object in motion, we're watching it change. But that's not the strangest part. One of the most discussed points about Atlas is its age. Based on its trajectory and chemical profile, many researchers believe it formed long before our solar system did. That means it has been traveling through interstellar space for an extremely long time, exposed to radiation, dust impacts, and the kind of cold that should freeze and lock every volatile material it has. Under those conditions, most objects lose their ability to show any noticeable activity. Their surfaces erode, their internal gases escape, and they eventually become inert. Yet Atlas is still releasing material. It's still reacting to heat. It still has compounds inside it that respond when warmed. This is what scientists refer to as the timeline problem. If Atlas is truly older than our solar system, why does it still contain active volatile layers? There are several working theories. Insulation. The outer layers of Atlas may be thick enough to protect deeper material from being stripped away. Low radiation travel path. It may have spent most of its journey in regions with less radiation exposure than expected. Compact internal structure. The nucleus could be denser or more stable than typical comets, preventing volatile loss. Each of these explanations could help account for the preserved internal chemistry, but they all point toward one broader possibility. Objects like Atlas may remain active far longer than we thought. And if that's the case, there may be more interstellar visitors passing through our system than the small number we've officially identified. Only most of them don't show enough activity to be noticed. The real question is how many we've already missed. As Atlas continues its path away from the Sun, the activity we're seeing now will gradually decrease. The coma will thin, the illumination will weaken, and the chemical signals will become harder to detect. This means the time frame to study Atlas while it's still active is limited. Because of that, researchers are working to capture as much information as possible while the object remains bright. Different observatories are coordinating so data isn't duplicated or lost. They're tracking how the gases change with distance, whether the glow remains stable, and how quickly the activity fades. These details help determine how Atlas is structured internally and how much volatile material remains beneath its surface. Another priority is refining the motion model. If Atlas continues to show small but consistent shifts in speed or direction, documenting those changes now is crucial. Later, when it's fainter, those measurements will be harder to confirm. A mission to physically approach or intercept Atlas isn't realistic at this stage. The object is already on an outbound trajectory, and mission planning would take longer than the window we have left. So everything we learn from Atlas will come from remote observation. The situation isn't urgent in a dramatic sense, but it is time-sensitive. Every week that passes, Atlas moves a little farther, and the signals we rely on become slightly weaker. So the focus right now is straightforward. Study Atlas while we still can. So after everything we've covered, this isn't just about Atlas as a single object anymore. It's about what Atlas represents. An interstellar body older than our solar system, still active and releasing material, challenges a lot of what we thought we understood about how these objects age and behave. If Atlas can maintain internal activity over a timescale this long, then our current models may not tell the full story. And that leads to the larger point. There may be many objects like this passing through space, but only a few ever get noticed. Some might never come close enough to the Sun to reveal their internal chemistry. Some might not produce enough visible activity to stand out. Atlas only became interesting because we happened to observe it under the right conditions. So, here's the question I want to leave you with. Do you think we've been underestimating how many of these interstellar travelers are actually out there? Let me know what you think. I always enjoy reading your interpretations. If you'd like to keep exploring these kinds of mysteries with me, stick around. Thanks for watching. See you in the next one.